In 1998, the universe felt a little emptier and a lot more dangerous. That year, two separate teams of astronomers confirmed something strange. The expansion of the universe was not slowing down. It was speeding up. This was a shock. It was like throwing a ball into the air and watching it accelerate away into the sky. To explain it, physicists revived an old idea from Einstein, the cosmological constant, a kind of energy inherent to the fabric of space itself. But this dark energy was a problem. It was too perfect, its value was incredibly small, so small that if it were any different, stars and galaxies would never have formed. Paul Steinhardt, a physicist at Princeton University, was not satisfied. This fine-tuning felt unnatural. So, in the same year, 1998, he and his colleagues Robert Caldwell and Rahul Dev proposed an alternative. They called it quintessence. Unlike the cosmological constant, quintessence was not a fixed number. You know, it was a dynamic, evolving field that filled all of space. It could change over time. And this idea carried a terrifying implication. Our universe might be living in a false vacuum. It is a state of seemingly low energy, but not the lowest possible energy. It is like a ball resting in a small divot on the side of a huge mountain. It is stable, for now, but a nudge could send it rolling down to the true bottom, the true vacuum. If a patch of our universe ever decayed into this true lower energy state, it would create a bubble. This bubble would expand at the speed of light. Inside, the laws of physics would be completely different. The fundamental constants that govern reality could change. Atoms might not be stable. Life would be impossible. The wall of this bubble would be an unstoppable wave of cosmic annihilation, wiping everything clean without warning. Steinhardt's work opened a door. It showed that the very stability of our existence could be tied to fields and forces we cannot see. And it pointed toward a deeper truth, one explored by an even more ambitious theory. The nature of these fields, the value of constants, and the stability of our vacuum might all be determined by something else. Something hidden just out of sight. They might be governed by the geometry of extra dimensions. Number 21, gravity's weakness is an illusion. The force of gravity is 10 undecillion times weaker than the electromagnetic force. In 1998, a paper by Nima Arkani Hamid, Savas Dimopoulos, and Gia Diwali proposed that extra dimensions could be as large as a millimeter across, a size detectable in tabletop experiments. The Large Hadron Collider has dedicated experiments searching for missing energy, a potential sign of particles escaping into these extra dimensions. Gravity is weak, incredibly weak. A small refrigerator magnet can hold a piece of paper against the gravitational pull of the entire Earth. This vast difference between gravity and the other fundamental forces, like electromagnetism and the nuclear forces, is a huge puzzle in physics. It is called the hierarchy problem. It asks why the scale at which gravity becomes strong, the Planck scale, is so much higher than the scale of the other forces. There seems to be no good reason for this enormous gap. It is like finding one person in a city is a trillionaire and everyone else has $1. It feels unnatural. M theory offers a strange and elegant explanation. The weakness is not real. It is a trick of perception. The idea is that our universe, the one we experience with its 3 spatial dimensions and one time dimension, is a membrane. And physicists call it a brane. This brane floats in a higher dimensional space called the bulk. Think of it like a sheet of paper in a large room. We live on the surface of the paper. All the particles and forces of the standard model electrons, quarks, photons, everything that makes up you and the world around you are stuck to this brane. They are like drawings on the paper, they cannot leave it, but gravity is different. Gravity is not a force of the brane, it is a property of the bulk, of the entire higher dimensional spacetime. The particle that carries the gravitational force, the graviton, is not confined to our brain. It can travel freely through all the extra dimensions. This is the key. Gravity is not weak because it is inherently feeble. It is weak because its influence is spread out over a much larger volume than we can perceive. The force lines of gravity radiate out into all the dimensions, not just our three. So here on our brane, we only feel a tiny fraction of its true strength. The rest of it has leaked away into the bulk. This is the basis of the ADD model, named for Arkani Hamed, Dimopoulos, and Diwali. Their work in the late 1990s revolutionized how physicists thought about extra dimensions. Before, it was assumed that if extra dimensions existed, they had to be incredibly small, curled up at the Planck scale, far beyond our ability to ever probe. The ADD model showed this was not the only option. The dimensions could be much larger, perhaps even up to a millimeter in size. Why a millimeter? Because that is the shortest distance at which we have accurately tested the strength of gravity. Experiments using tiny, precisely engineered torsion balances have measured gravity's pull between small masses. Below a millimeter, it is a blind spot. If the ADD model is correct, it has testable consequences. One is that at very short distances, gravity should get stronger much faster than we expect. Newton's inverse square law, which works perfectly for planets and apples, would break down. Instead of the force weakening by a factor of 4, when you double the distance, it might weaken by a factor of 8 or 16, depending on the number of extra dimensions. Those torsion balance experiments are looking for exactly this kind of deviation. So far, they have found nothing, which places increasingly tight limits on how large these dimensions can be. Another consequence could show up at particle colliders like the Large Hadron Collider LHC. When protons are smashed together at enormous energies, that energy can be converted into new particles. According to the ADD model, some of that energy could create gravitons, but because these gravitons can travel in the bulk, they would immediately fly off our brane and disappear into the extra dimensions. From our perspective, it would look like energy has simply vanished from the collision. The detectors would see an imbalance, the energy going in would not match the energy of the particles coming out. This missing energy signature is a key target for searches at the LHC. So far, no definitive signal has been found. But the possibility remains that extra dimensions are not just a mathematical concept. They could be a physical space into which gravity, the most familiar force, is constantly disappearing. Number 20, dark matter is just matter in another dimension. Fritz Zwicky first proposed the existence of dunkel materie, or dark matter, in 1933 after observing that the Coma Galaxy cluster was rotating too fast for the amount of visible matter it contained. Roughly 85% of all matter in the universe is dark matter. We know it is there only because of its gravitational effects. Kaluza-Klein particles, a predicted consequence of extra dimensions, have properties that make them an almost perfect candidate for dark matter. The universe has a weight problem. When astronomers look at galaxies, they see them spinning so fast that they should fly apart. The gravity from all the visible stars, gas, and dust is not nearly strong enough to hold them together. When they look at clusters of galaxies, they see the same thing. The galaxies are moving around so quickly that the cluster should have disintegrated billions of years ago. There is something else there, something invisible, something massive, providing the extra gravitational glue. They call it dark matter. It is not just a little bit of extra stuff. Dark matter outweighs all the normal matter, everything that makes up planets, stars, and people by more than 5 to 1. It is the dominant form of matter in the cosmos, yet we have no idea what it is. We know what it is not. It is not made of atoms. It does not interact with light, which is why we cannot see it. It seems to pass through normal matter like a ghost. For decades, the leading candidates have been hypothetical particles with names like WIMPs, weakly interacting massive particles, or actions. Despite huge, expensive experiments built deep underground to detect them, none have been found. Or M theory provides a completely different kind of answer. What if dark matter is not some exotic new particle within our dimensions? What if it is perfectly ordinary matter, but it is located somewhere else? This idea stems from a concept that predates M-theory, going back to the 1920s with the work of Theodor Kaluza and Oskar Klein. They were the first to seriously propose that an extra dimension could exist. They showed that if you add a fifth dimension to Einstein's theory of general relativity, you get back the original theory plus something extra, the equations for electromagnetism. It was a stunning unification, but it came with a prediction. Any particle that can travel in this extra dimension would appear to us in our 4 dimensions as a series of copies. There would be the normal particle, and then a whole tower of heavier versions of that same particle. These are called Kaluza-Klein KK particles. Each particle in the tower corresponds to a different amount of momentum the particle has in the extra dimension. From our 4D perspective, this momentum in a hidden direction looks just like mass. The more momentum, the heavier the particle appears. Now apply this to the brane world scenario. Most particles are stuck on our brane, but what if some are not? What if there are other branes parallel to our own, separated by a tiny distance in the bulk? Or what if some particles can, like gravitons, travel in the bulk? A particle on a nearby brane or a KK particle moving in the bulk would be invisible to us. We could not touch it or see it because it is not on our brane. Our forces, like electromagnetism, are confined to our sheet of reality. But we would feel its gravity. Gravity, as the force of space-time itself, permeates the entire bulk. So this shadow matter in another dimension would exert a gravitational pull on our own. It would cluster in the same way, forming halos around galaxies and holding galaxy clusters together. It would behave exactly like dark matter is observed to behave. It would be massive and visible and interact with our world only through gravity. The lightest of these Kalu-Klein particles is a prime dark matter candidate. If it is stable, it would have been produced in the hot, early universe and would still be around today, forming the vast cosmic structures we see. Experiments like the LHC are searching for these KK particles. If they exist, they could be created in high-energy collisions. They would then decay back into standard model particles, leaving a distinct signature. Finding them would not just solve the mystery of dark matter, it would be concrete evidence that we are not alone in the cosmos, not in the sense of aliens, but in the sense of being just one slice of a much larger, higher dimensional reality. Number 19, the universe did not start from a point. It started from a collision. The Big Bang Theory predicts a singularity, a point of infinite density and temperature, which most physicists believe is a sign the theory is incomplete. In 2001, Paul Steinhardt, Bert Overoot, Justin Shuri, and Neil Turok proposed the ekpyrotic universe model, where the Big Bang was caused by the collision of 2 branes in a higher dimension. The name ekpyrotic comes from the ancient Greek Stoic belief in a cosmic fire that cyclically destroys and recreates the world. The story of creation, we are all told, is the Big Bang. The universe began as an infinitesimally small, infinitely hot, and infinitely dense point called a singularity. From this point, it exploded outwards, expanding and cooling over 13.8 billion years to become the cosmos we see today. It is a powerful and successful theory. It explains the expansion of the universe, the cosmic microwave background radiation, and the abundance of light elements like hydrogen and helium. But it has problems. That initial singularity is a point where the laws of physics as we know them break down completely. General relativity ceases to make sense. The theory cannot explain what happened at time 0 or what came before it. To patch this up, physicists added the idea of inflation, a period of hyperfast expansion in the first fraction of a second. Inflation solves many problems, but it has its own issues. It seems to require very specific, fine-tuned conditions to get started. And once it starts, it tends to go on forever, creating a messy multiverse of pocket universes that is difficult to test. Or M theory's brane world scenario offers a radical alternative. It suggests there was no singularity. There was no beginning to time. The event we call the Big Bang was not the creation of the universe, but a violent transitional moment in a much grander, potentially eternal cycle. This is the core of the ekpyrotic and cyclic models. In this picture, our universe is one of two parallel branes separated by a tiny gap in a fifth dimension. These two branes are not necessarily static, they can move. For eons, the two branes are cold, empty, and nearly parallel. But there is a force between them, a kind of spring-like potential energy. This force slowly pulls the branes together. As they approach, they contract. After an immense period of time, they collide. The collision is not at a single point, but all across the vast, infinite surfaces of the branes. This impact releases a tremendous amount of kinetic energy, converting it into a hot, dense plasma of particles and radiation on each brane. This hot, dense state is what we interpret as the Big Bang. From that moment on, the story proceeds much as standard cosmology describes. The brane expands, it cools, particles form atoms, atoms clump into stars and galaxies. But the origin is completely different. The universe is not born from nothing in a singularity. It is reborn from the collision of pre-existing dimensions. After the collision, the branes bounce apart. The force between them pushes them away again. As they separate, they expand and cool for trillions of years. During this long dark phase, the universe becomes nearly empty as everything spreads out. But the force between the branes eventually slows their separation, stops it, and begins to pull them back together again. The cycle repeats. A slow contraction, a collision, a bang, and a long expansion. This model has several advantages. It avoids the singularity. It provides a natural explanation for the universe's flatness and uniformity without needing the special conditions of inflation. The collision itself smooths out the branes. It also makes different predictions. For example, it suggests that gravitational waves from the very early universe should be much weaker than those predicted by inflation. And future experiments designed to detect these primordial gravitational waves could distinguish between the two theories. If the cyclic model is correct, it means the dimensions are not just all around us, they are the engine of cosmic time, the mechanism that allows the universe to be born, to die, and to be reborn again and again. Number 18, black holes could be passageways to other dimensions. The concept of a gravastar, proposed in 2001 by Paul Mazur and Emil Mutola, suggests that instead of a singularity, a black hole might contain a core of exotic dark energy, avoiding the information loss paradox. A 2019 study suggested that the strange behavior of the object G2 near our galaxy's supermassive black hole could be explained if it were a star with a smaller black hole inside it, a so-called black hole star. Stephen Hawking's final theory, published posthumously in 2018, proposed that black holes might not have event horizons in the classical sense, but apparent horizons that could allow information to escape. Black holes are the most extreme objects in the universe. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. According to Einstein's theory of general relativity, at the center of a black hole lies a singularity, a point of zero volume and infinite density where the laws of physics are destroyed. This has always been a point of discomfort for physicists. It is another sign that our theories are incomplete. The problem gets worse when you add quantum mechanics to the picture. One of the fundamental rules of quantum mechanics is that information can never be truly lost. But if you throw something into a black hole, a book, an encyclopedia, a computer, it seems to be gone forever. The black hole itself eventually evaporates over immense timescales through a process called Hawking radiation. But this radiation is predicted to be random, thermal noise. It contains no information about what fell in. This is the black hole information paradox. It is a deep conflict between our two best theories of the universe. The M theory's extra dimensions offer a way out. What if the singularity is not the end of the line? In some brain world models, a black hole on our brain is not just a collapsed star. It is a connection to the bulk, the higher dimensional space. The immense gravity of the collapsed star could warp space-time so severely that it punches a hole, or a throat, through our brain and into the bulk. In this scenario, matter that falls into a black hole does not get crushed into a singularity. Instead, it might travel through this throat and emerge into the higher dimensional space. Or it could even emerge onto another parallel brain. The information is not destroyed, it is just removed from our universe. This would resolve the information paradox in a radical way. A black hole would not be a cosmic incinerator, but a cosmic escape hatch. This idea is not just a fantasy, it has potentially observable consequences. If black holes are gateways to the bulk, they might not behave exactly as general relativity predicts. For example, when two black holes merge, they send out ripples in spacetime called gravitational waves. Telescopes like LIGO and Virgo have detected these waves, and they match the predictions of Einstein's theory with stunning accuracy. But there could be subtle differences. If some energy from the merger leaks into the extra dimensions in the form of gravitons, the signal we receive could be slightly weaker than expected. Another possibility is gravitational wave echoes. After the main burst of waves from a merger, there might be a series of smaller, fainter echoes. These could be caused by the waves bouncing around in the warped spacetime near the black hole's event horizon, which might have a more complex structure than we think if extra dimensions are involved. Some researchers have claimed to see tentative evidence of these echoes in the LIGO data, though the claims are highly controversial and require much more evidence. Furthermore, if tiny microscopic black holes could be created at the LHC, their decay would look very different. Instead of evaporating via Hawking radiation primarily into particles on our brain, they would evaporate mostly into the bulk. They would disappear very quickly, leaving a very clean, distinct signature of missing energy. The search for such events is ongoing. The idea that every black hole, from the smallest to the supermassive giants at the centers of galaxies, might be a physical portal to a larger hidden reality is a profound one. The dimensions would not just be around us, but also contained within the darkest, most mysterious objects in our own universe. Number 17, the constants of nature might not be constant. In 1999, a team of astronomers studying light from distant quasars found evidence that the fine structure constant, which governs the strength of electromagnetism, may have been slightly weaker 10 billion years ago. The Oklo Natural Nuclear Reactor, a uranium deposit in Gabon, Africa, that sustained a spontaneous chain reaction 1.7 billion years ago, provides a deep time test of these constants. The reactions that occurred there were highly sensitive to the fine structure constant, and the data suggests it has not changed significantly. String theory allows for the constants of nature to be dynamic fields, not fixed numbers. The laws of physics are built on a foundation of numbers. These are the fundamental constants of nature. The speed of light c, the gravitational constant g, Planck's constant h, the charge of an electron e. These numbers appear in all of our equations, we measure them with incredible precision, and we assume they are just that constant, the same everywhere in space, and the same at all times from the Big Bang to the present day. But well, why should they be? We have no fundamental theory that explains why these constants have the specific values they do. We just measure them and plug them in. M-theory challenges this assumption head-on. In the context of string theory and M-theory, these numbers are not fundamental at all. They are the result of something deeper, the geometry of the extra dimensions. The theory requires extra spatial dimensions to be mathematically consistent, typically 6 or 7 of them. But we do not see them, so they must be hidden. The standard explanation is that they are compactified or curled up into a tiny, complex shape at every point in our space. The shape of this internal manifold is incredibly important. It is not just some random ball. It has a complex geometry with twists, turns, and holes. A class of shapes often considered are called Calabi-Yau manifolds. The precise size and shape of this compactified space determines the physics we see in our large dimensions. The way strings can vibrate within this space dictates the kinds of particles that can exist and their properties like mass and charge. The effective strength of the forces we measure, like electromagnetism and gravity, depends on the volume and curvature of these tiny dimensions. This means that our beloved constants are not truly constant. They are, in M-theory's language, moduli. They are fields whose values are determined by the configuration of the extra dimensions. And if the dimensions can change, so can the constants. If the volume of the compactified dimensions were to slowly increase over cosmic time, for example, the gravitational constant g would appear to us to get weaker. If the shape of the manifold were to subtly warp, the fine structure constant might change. This is a testable prediction. Astronomers can look back in time by observing light from distant objects like quasars. The light from a quasar billions of light years away has been traveling for billions of years. When it arrives at our telescopes, it carries a snapshot of the laws of physics at that earlier time. By analyzing the spectral lines in this light, the specific frequencies at which atoms absorb light, scientists can measure the value of the fine structure constant in the distant past. Some studies, like the one from 1999, have claimed to find evidence for a small change. The results are debated and controversial, with other studies finding no change at all. The measurements are incredibly difficult, but they represent a direct way to probe the stability of the extra dimensions. The Oklo natural reactor provides another such probe. By analyzing the isotopic ratios of the leftover materials from this 2 billion-year-old nuclear reaction, scientists can deduce the strength of the nuclear forces and electromagnetism at that time. The results from Oklo strongly suggest that the constants have been very stable. However, this does not rule out the idea. It may be that the extra dimensions are currently stuck in a stable configuration. The potential energy landscape for these moduli fields could have many valleys, and our universe happens to be sitting in a deep one. But it might not be the deepest one. A powerful enough event could knock us out of this valley and into another, causing the constants of nature to shift suddenly. This is related to the idea of vacuum decay. The stability of our physical laws could be tied to the geometric stability of dimensions we can never directly see. Number 16, every particle is a note on a higher dimensional guitar string. The original bosonic string theory of the 1970s required 26 space-time dimensions to be consistent. The inclusion of fermions matter particles in superstring theory reduced this requirement to 10 space-time dimensions. An M theory, proposed by Edward Witten in 1995, unified the 5 competing superstring theories by positing an 11th dimension. At the heart of our current understanding of physics is a zoo of fundamental particles. Electrons, quarks, photons, gluons, neutrinos, the Higgs boson. The standard model of particle physics lists them out, describes their properties, and explains how they interact. It is incredibly successful, but it is not very satisfying. It does not explain why this particular set of particles exists, or why they have the masses and charges that they do. It treats them all as fundamental, indivisible points. String theory replaces this picture with something much simpler and, in a way, more musical. The fundamental entities of the universe are not point particles. They are tiny, one-dimensional, vibrating filaments of energy called strings. These strings can be closed loops, like a rubber band, or open-ended, like a piece of twine. They are incredibly small, on the order of the Planck length, which is about 10 raised to the power of 35 meters. That is as small compared to an atom as an atom is to our solar system. This is why we perceive them as points. Everything in the universe, every particle of matter, every carrier of force, is just a different vibration of these fundamental strings. Just like a guitar string can be plucked to produce different musical notes, a fundamental string can vibrate in different patterns. One pattern of vibration appears to us as an electron. Another, different pattern of vibration appears as a photon. Another, a quark. The entire particle zoo is reduced to a single concept, a symphony of vibrating strings. The properties of the particle are determined by the properties of the vibration. The energy of the vibration determines the particle's mass, according to E equals mc raised to the power of 2. The way the string interacts with other strings determines its charge. This elegant idea unifies matter and forces in a natural way. But there is a catch for the mathematics of this theory to work out. For it to be self-consistent and free of paradoxes, it requires that the strings are not vibrating in our familiar 3 spatial dimensions. They need more room to move. The math demands the existence of extra dimensions. The most successful versions of the theory, superstring theories, require a total of 10 space-time dimensions, 9 of space, and 1 of time. An M theory, which unifies these, requires 11. These extra dimensions are where the richness of the vibrations comes from. The string can wiggle in our familiar directions, up, down, left, right, forward, back. But it can also wiggle in the 4th spatial dimension, the 5th, the 6th, and so on. Each of these extra directions of vibration corresponds to a different kind of particle. The complex geometry of these hidden dimensions, the Calabi-Yau manifold, acts like the body of the guitar. It shapes the resonances and determines which notes or particles are stable and can exist in our universe. So when you look at a rock, a tree, or your own hand, you are not seeing a collection of tiny, solid points. You are seeing a fantastically complex and harmonious orchestra of countless tiny strings. Their vibrations are what create the illusion of substance, charge, and mass, and the music they play is only possible because they are vibrating in a space with more dimensions than we can see. The very existence of the matter that makes up our world could be the most direct evidence that those dimensions are real and are all around us, curled up and hidden at every single point in space. Number 15, we are living in a hologram. In 1997, physicist Juan Maldacena proposed the ADS-CFT correspondence, a concrete realization of the holographic principle. It shows a perfect mathematical duality between a string theory in a 5-dimensional, negatively curved spacetime anti-de Sitter space and a quantum field theory without gravity on its 4-dimensional boundary. The information density of a black hole's event horizon is about 10 raised to the power of 69 bits per square meter. A team at Fermilab is currently running an experiment called the holometer, using powerful lasers and interferometers to look for a fundamental holographic noise, a jitter in spacetime itself that would be evidence for this principle. We think of the world as being 3-dimensional. It has length, width, and height. Everything we see and interact with exists within this 3D space. But what if this is an illusion? What if the reality we experience is just a projection, a hologram generated from information stored on a distant 2-dimensional surface? This is the holographic principle, one of the most profound and bizarre ideas to come out of the study of black holes and string theory. The idea started with black holes. Jacob Bekenstein and Stephen Hawking discovered that the amount of information a black hole can contain, its entropy, is not proportional to its volume, as you would expect. It is proportional to the surface area of its event horizon, the 2-dimensional boundary from which nothing can escape. This was a shocking result. It is as if all the information about the 3D interior of the black hole is somehow encoded on its 2D surface. Gerard Hooft and Leonard Susskind took this idea and ran with it. They proposed that this might not be just a property of black holes, but a fundamental principle of the entire universe. The holographic principle states that the description of a volume of space can be thought of as encoded on a lower dimensional boundary to that region. In its most extreme form, it suggests that our entire 3-dimensional universe could be a holographic projection of physical processes happening on a distant two-dimensional screen. This sounds like science fiction, but Juan Maldacena gave it a solid mathematical foundation with his ADS-CFT correspondence. He discovered a precise mathematical dictionary that translates between two very different looking theories. One is a string theory that includes gravity existing in a 5D bulk space. The other is a quantum field theory, like the one used to describe particle physics, that does not include gravity and lives on the 4D boundary of that space. The math showed that every statement, every calculation, every physical process in the 5D gravity theory had a corresponding equivalent statement in the 4D boundary theory. They are two different descriptions of the same underlying reality. This has huge implications. It suggests that space-time and gravity might not be fundamental, they might be emergent phenomena. The real fundamental physics might be happening on this lower dimensional boundary, and the 3D space, the extra dimension of depth and the force of gravity are all part of the hologram projected from it. If this is true, it could mean that space-time itself is not smooth and continuous. It would be made of fundamental pixels or bits of information on the order of the Planck length. The universe would have a finite resolution, like a digital image. We do not notice this because the pixels are incredibly small. But it might be detectable. The Fermilab holometer was designed to look for this. The idea is that if our 3D space is a projection from a 2D surface, there might be an inherent uncertainty or jitter in the position of things, a kind of fundamental holographic noise. The experiment used two identical high-power interferometers to try to detect this tiny random motion in space-time itself. The initial results did not find the predicted noise, but the search continues and has placed limits on certain models. The holographic principle provides a powerful tool for physicists. Difficult calculations in one theory can sometimes be translated into much easier calculations in the other. It has been used to study problems in particle physics and even condensed matter physics. But its true meaning is deeply philosophical. It suggests that the dimensions we perceive might not be the fundamental ones. Our entire universe, with its vastness and depth, could be a richly detailed but ultimately flat image painted on the boundary of a higher dimensional space. Number 14, parallel universes are separated by a millimeter. The Randall-Sundrum model, proposed in 1999 by physicists Lisa Randall and Raman Sundrum, does not require the extra dimension to be large in the same way the ADD model does. Instead, it can be infinitely large but highly warped. A 2015 experiment at the Institut Laue-Langevin in Grenoble, France, searched for neutrons disappearing into a parallel brane. They found no evidence setting new limits on the scale of such interactions. The idea of parallel universes is a staple of science fiction. But in the context of M-theory, it is a serious physical possibility. The brane world scenario does not just allow for one brane, our universe, floating in a higher dimensional bulk. It allows for many of them. There could be an infinite stack of branes, like pages in a book, each a self-contained universe with its own matter, its own forces, and perhaps even its own slightly different laws of physics. We are confined to our page. We are made of standard model particles, which are the endpoints of open strings, and these strings have their ends stuck firmly to our brane. We cannot leave, we cannot see the other pages or interact with them directly, but they could be incredibly close. In some models, the distance between our brane and a neighboring one could be less than a millimeter. Another universe could be right here, in this room, separated from you by a distance smaller than the thickness of a piece of paper, but in a direction you can never point to the fourth spatial dimension. The only force that can bridge this gap is gravity. Because gravity is a property of the bulk spacetime, it can travel between the branes. This means we could, in principle, feel the gravitational pull of matter in that other universe. This offers a potential explanation for dark matter. The dark matter in our galaxy's halo might not be in our galaxy at all. It could be a parallel galaxy located on a nearby brane whose gravity is leaking across the dimensional gap, and holding our own galaxy together. Lisa Randall and Raman Sundram came up with a particularly clever version of this idea. Their RS-1 model proposed a warped fifth dimension. In this model, space-time is not flat. It is intensely curved in the extra dimension. There are two branes. One is the gravity brane, or Planck brane, where gravity is fundamentally strong. The other is our brane, the TV brane, where we live. Because of the extreme warping of space-time between the branes, gravity is exponentially weakened by the time it reaches us. This warping provides an elegant solution to the hierarchy problem without needing large, flat, extra dimensions. Gravity is weak for us because we are far away from its source on the gravity brane through a warped dimension. This model makes specific predictions. It suggests the existence of Kaluza-Klein gravitons, but with a different mass spectrum than in the ADD model. These heavy gravitons could be produced at the LHC. If a KK graviton is created in a proton-proton collision, it would quickly decay into familiar particles, like a pair of electrons or photons. This would create a resonance, a bump in the data at a specific energy corresponding to the mass of the KK graviton. Searches for such resonances are a major focus of experiments at the LHC. So far, none have been found, pushing the possible mass of these particles higher and higher. Another, more direct experiment was the one conducted in Grenoble. The idea was to see if neutrons, which are neutral particles, could be induced to oscillate into a parallel universe. A beam of slow-moving neutrons was sent towards a detector. If a parallel brane were very close, there would be a small but non-zero probability that a neutron could tunnel across the dimensional gap and disappear from our universe. The experiment involved carefully counting the neutrons at the source and at the detector. If fewer neutrons arrived than were sent, it could be a sign of this interdimensional travel. The experiment found no missing neutrons, which put strong constraints on how strongly our world can be coupled to a parallel one. Despite the null results so far, the possibility remains a tantalizing one. An entire universe, perhaps much like our own, could be hovering just out of reach. Number 13, the laws of physics are an environmental accident. String theory does not predict a single, unique vacuum state for the universe. Instead, it suggests a vast landscape of at least 10 raised to the power of 500 possible different vacuum states, each corresponding to a different way to compactify the extra dimensions. In 2003, Leonard Susskind first articulated the idea that the string theory landscape combined with eternal inflation leads almost inevitably to an anthropic explanation for the value of the cosmological constant. The observed value of dark energy is about 120 orders of magnitude smaller than the value predicted by quantum field theory. For centuries, the goal of physics has been to find the one true set of laws that govern the universe. The assumption has always been that if we just dig deep enough, we will find a final theory, a single set of equations from which everything else can be derived. We hoped this theory would explain why the fundamental constants have the values they do, why there are 3 generations of particles, and why we live in 3 spatial dimensions. M theory, in its current form, shatters this dream. It does the opposite. Instead of predicting a unique universe, it predicts a staggering number of possible universes. This arises from the problem of compactification. The theory requires 10 or 11 dimensions. To get to our 4-dimensional world, the extra 6 or 7 must be curled up into a small shape. But there is no principle within the theory that tells us which shape to pick. And it turns out there are a colossal number of possible shapes. The number of self-consistent ways to compactify the extra dimensions, each resulting in a different set of physical laws in the large dimensions, is estimated to be at least 10 raised to the power of 500. This is a number so large it is difficult to comprehend. It is a 1 followed by 500 zeros. There are only about 10 raised to the power of 80 atoms in the entire observable universe. Each of these 10 raised to the power of 500 possibilities corresponds to a different vacuum state, a different stable or metastable configuration of the universe. Each one would have its own set of fundamental constants, its own particle spectrum, its own number of large-scale dimensions. This collection of all possible universes is called the string theory landscape. This is a deeply unsettling idea for many physicists. It suggests that the laws of nature as we know them are not unique or fundamental. They are an accident of our location. It is a kind of cosmic geography, just as the local climate and geology are different in different places on Earth. The local laws of physics might be different in different parts of the multiverse. We happen to live in a pocket of the multiverse where the extra dimensions curled up in a way that produced the physics we see. This provides a controversial but powerful explanation for some of the fine-tuning problems in cosmology, especially the value of the cosmological constant dark energy. This value is absurdly small. Quantum theory predicts a value that is about 10 raised to the power of 120 times larger than what we observe. This is the worst prediction in the history of physics. In the landscape picture, there is no one prediction. The cosmological constant can take on a whole range of different values in different universes. Most of them would have a large value, either positive or negative. A large positive value would cause the universe to fly apart so quickly that galaxies could never form. A large negative value would cause it to collapse back on itself in a fraction of a second. Only in a tiny fraction of these 10 raised to the power of 500 universes would the cosmological constant be small enough to allow for the formation of complex structures like galaxies, stars, and ultimately life. So we find ourselves living in such a universe for the simple reason that we could not exist to ask the question anywhere else. This is the anthropic principle. It is not a prediction, but a selection effect. This idea is deeply divisive. To its critics, it is a cop-out, an admission that physics has given up on explaining why the universe is the way it is. To its proponents, it is the logical conclusion of combining string theory with cosmology. The geometry of the extra dimensions is not just around us, it is the source of a vast cosmic lottery, and we just happen to live in a universe that drew a winning ticket for life. Number 12. Time might have more than one dimension. In 1995, physicist Itzhak Bars proposed a two-time physics model where all physical phenomena can be described by a more fundamental theory set in a space-time with two time dimensions and four space dimensions. The F-theory formulation of M-theory, developed by Qumrun Vafa, naturally lives in a 12-dimensional space that includes two time-like dimensions. The signature of this space-time is 10-2. We experience time as a one-way street. It flows inexorably forward, from past to present to future. In physics, time is treated as the fourth dimension, woven together with the three dimensions of space into a fabric called space-time. But it is always just one dimension of time. The idea of having more than one time dimension sounds like pure fantasy, the stuff of confusing time travel plots. But some advanced physical theories suggest it might be a real possibility. The primary objection to multiple time dimensions has always been causality. In a world with two or more time dimensions, you could, in principle, create closed time like curves. This means you could travel in a loop and return to your own past, leading to all the familiar paradoxes of killing your grandfather. The universe would lose its predictable causal structure. However, some physicists have found clever ways around this. Itzhak Bar's two-time physics is one example. He showed that you can formulate a theory in a four-space, two-time, four-Plateau-dimensional world that, through a process of gauge symmetry, produces the standard three-space, one-time, three-plane physics we observe. The extra time dimension and an extra space dimension are not curled up in the usual sense. Instead, they are hidden from us by the symmetries of the theory. The shadow of this higher dimensional world is the world we see. This more symmetric, higher dimensional framework can solve some technical problems in the standard model and offer new perspectives on physical laws. M-theory also hints at multiple time dimensions. One of the most mysterious formulations of the theory is called F-theory. It is used to describe certain complex situations that are difficult to handle in the standard 11-dimensional M theory. Mathematically, F theory is most naturally formulated in a 12-dimensional space. This space has 10 spatial dimensions and 2 time dimensions. This second time dimension is not like the first. It is treated differently in the mathematics. It is often described as being part of a torus or donut shape along with one of the spatial dimensions. The geometry of this torus determines key features of the resulting physical theory. But the fact that it is a time-like dimension is significant. What would it mean if a second time dimension were real? It is hard to say. Our perception is so strongly tied to a single flow of time that it is difficult to imagine an alternative. Some speculative ideas suggest that phenomena we find mysterious in 1/3 dimensions might be simpler if viewed from a higher dimensional time perspective. Perhaps quantum uncertainty, the probabilistic nature of reality at the smallest scales, is a result of us only seeing a slice of a more deterministic reality that exists in 2-time. Another idea is that this second time dimension could be cyclic or loop-like. This could potentially lead to cyclic models of the universe without needing colliding branes. The universe could be evolving not just along a line of time, but around a loop in a second time direction. This is one of the most speculative areas of theoretical physics. There is no experimental evidence for a second time dimension, but it is a possibility that emerges from the mathematics of our most advanced theories. It suggests that our most fundamental experience, the passage of time, might itself be just a sliver of a much more complex temporal reality. The extra dimensions might not just be spatial, they could be temporal as well. Number 11, quantum entanglement is a bridge through the bulk. The ER=ER conjecture was proposed by Leonard Susskind and Juan Maldacena in 2013. ER stands for Einstein-Rosen bridges wormholes, and EPR stands for Einstein-Podolsky-Rosen, the authors of the famous 1935 paper on quantum entanglement. The temperature of a black hole's Hawking radiation is inversely proportional to its mass. For a solar mass black hole, this temperature is only about 60 nanokelvins, far colder than the cosmic microwave background. Quantum entanglement is what Albert Einstein famously called spooky action at a distance. It is one of the strangest and most well-verified aspects of quantum mechanics. You can take two particles, like electrons, and link them together in a special way. Then you can separate them, sending one to the other side of the room or the other side of the galaxy. The moment you measure a property of one particle, like its spin, you instantly know the corresponding property of the other particle. It is as if they are communicating with each other faster than the speed of light, which should be impossible. This phenomenon has been experimentally confirmed over and over. It is the basis for technologies like quantum computing and quantum cryptography. But it remains deeply mysterious. How do the particles know about each other instantly across vast distances? The ER=EPR conjecture offers a mind-bending explanation rooted in the geometry of extra dimensions. It proposes that two entangled particles are, in a very real sense, connected by a wormhole. A wormhole, or an Einstein-Rosen bridge, is a theoretical shortcut through spacetime. It is a tunnel with two mouths that could be in different places in the same universe. The conjecture suggests that when two particles are entangled, a non-traversable wormhole forms between them through the higher dimensional bulk of spacetime. This is not a wormhole you can send a spaceship through. It is a tiny quantum-scale connection. The connection is what creates the spooky correlation. The particles are not sending signals to each other through our space. They are touching or are part of the same object through a hidden dimension. The distance between them in our 3D space is irrelevant because they are connected by a direct path through the bulk. This idea comes from studying the relationship between black holes and entanglement in the context of the holographic principle. Imagine you create a pair of entangled particles and you throw one into a black hole while keeping the other one outside. That particle is now entangled with the black hole. Now imagine you have two black holes and you collect the Hawking radiation they emit. If you could capture all the radiation from both, you might find that a particle emitted by the first black hole is entangled with a particle emitted by the second. According to ER equals CPR, these two entangled black holes would be connected by a wormhole. This provides a new way to think about space-time itself. Perhaps space-time is not fundamental. Perhaps it is built up from entanglement, the vast web of quantum entanglement between all the particles in the universe might be what knits the fabric of space-time together. The geometry we experience, the very meaning of distance and location, could be an emergent property of these quantum connections. If this is true, then every time an entangled pair of particles is created in a lab, a tiny, microscopic bridge is being formed through a higher dimension. These dimensions are not just a passive backdrop. They are an active medium, a space where quantum connections manifest as geometric tunnels. The weirdness of the quantum world and the geometry of space-time might be two sides of the same coin, a coin minted in the bulk of a higher dimensional reality. Number 10, the Big Bang's afterglow hides scars of other dimensions. The cosmic microwave background CMB is the oldest light in the universe, emitted when the universe was just 380,000 years old. The Wilkinson Microwave Anisotropy Probe WMAP and the Planck satellite have mapped the tiny temperature fluctuations in the CMB to a precision of a few parts in a million. In 2007, a feature known as the CMB cold spot, an unusually large and cold region of the sky, was identified as a potential sign of a collision with another bubble universe. The cosmic microwave background is a baby picture of our universe. It is a faint glow of radiation that fills all of space, a leftover heat from the Big Bang. When we look at the CMB, we are looking back in time to an era when the universe was a hot, dense soup of particles and radiation. Tiny variations in the temperature of this ancient light, first discovered in 1992, are the seeds that grew into all the galaxies and cosmic structures we see today. Our standard cosmological model, which includes inflation, does an excellent job of explaining the statistical properties of these temperature spots. It predicts a random Gaussian pattern of hot and cold spots, and this is largely what we see. But there are a few strange anomalies, features in the CMB map that do not seem to fit the standard picture perfectly. One of these is the CMB cold spot. It is a patch of the sky that is significantly colder and larger than is likely to occur by random chance. Brain world cosmology offers a possible explanation for features like this. If our universe is a brane that exists in a higher dimensional bulk, it might not be alone. As discussed in the context of the multiverse, there could be other bubble universes, other branes out there. It is possible that in the distant past, our universe collided with one of these other universes. Such a collision would have been a cataclysmic event. It would have left a lasting mark, a bruise on our universe. This bruise would manifest as a disturbance in the early plasma, which would then be imprinted onto the cosmic microwave background. Here, a collision with another bubble universe could, in theory, produce a large circular pattern in the CMB, a disk that is either hotter or colder than its surroundings. The CMB cold spot has been seriously considered as a possible candidate for such a scar. The calculations are complex and the statistical evidence is not definitive. It is entirely possible that the cold spot is just a rare statistical fluke, the cosmic equivalent of getting dealt a royal flush. But if it is the remnant of an inter-universal collision, it would be the first direct evidence of dimensions beyond our own. Another way extra dimensions could leave their mark on the CMB is through the behavior of gravity. In brane world models where gravity can leak into the bulk, this leakage would have been present in the early universe. This would affect how the primordial density fluctuations grew, and this in turn would alter the pattern of spots in the CMB. The precise details of the CMB's temperature and polarization patterns are sensitive to the laws of gravity at the earliest times. By comparing the high-precision data from the Planck satellite with the predictions of these models. Cosmologists can place tight constraints on the properties of any extra dimensions. So far, the data from the CMB is perfectly consistent with standard 4D general relativity. There is no smoking gun evidence for extra dimensions in the afterglow of the Big Bang. But the search continues. Hidden within the faint microwave static that pervades the cosmos, there could be a message. It could be a message telling us that our universe is just one of many, and that the space between them is real. Number 9. Faster than light travel might be possible, but not in the way you think. In 1994, physicist Miguel Alcubierre proposed a warp drive metric for general relativity that allows for faster than light travel without violating local relativity. It requires exotic matter with negative energy density. In M-theory, the Casimir effect, which produces a small attractive force between two uncharged parallel plates in a vacuum, is a real-world example of negative energy density. This effect was first measured experimentally in 1996 by Steve Lamoureux. The speed of light in a vacuum, about 300,000 kilometers per second, is the ultimate speed limit in our universe. Einstein's theory of special relativity makes it clear nothing with mass can reach this speed, let alone exceed it. It would take an infinite amount of energy. Like, this is a huge barrier for interstellar travel. The nearest star system, Alpha Centauri, is over 4 light years away. A trip there would take generations. But what if you could cheat? What if you could travel faster than light without actually breaking the local speed limit? This is the idea behind the Alcubierre warp drive. It is a theoretical solution to Einstein's equations that involves creating a warp bubble around a spaceship. Inside the bubble, space-time is flat and the ship is stationary. It is not moving at all, so it does not violate any physical laws. The trick is what happens to space-time outside the bubble. The drive would work by contracting space-time in front of the ship and expanding space-time behind it. The ship itself does not move through space. Space itself is moved around the ship. It is like a surfer on a wave. The surfer is not moving faster than the water in the wave, but the wave itself carries the surfer across the ocean. The warp bubble would carry the ship across the cosmos, potentially at many times the speed of light. There is a huge catch. To create this distortion of space-time, you need matter with a negative energy density. All the matter and energy we know of, stars, planets, light, radiation, has a positive energy density. Negative energy is bizarre, exotic stuff. It would have strange properties like having gravity that repels instead of attracts. This is where extra dimensions might come in. While creating large amounts of stable negative energy seems impossible in our normal 3-plane dimensional world, it might be more feasible in a higher dimensional context. That some M-theory models, particularly those with warped geometries like the Randall-Sundrum model, involve fields and stresses in the bulk space-time that could behave like negative energy from our 4D perspective. The very mechanism that stabilizes the distance between branes in some cyclic universe models relies on a kind of negative pressure or phantom energy. It is possible that by manipulating the geometry of the extra dimensions on a local scale, one could generate the required negative energy effect in our dimensions. This would be technology far beyond anything we can currently conceive. It would involve manipulating the fabric of reality at the Planck scale. But M-theory at least provides a potential physical source for the exotic ingredient needed for a warp drive. Another related idea is using extra dimensions as a literal shortcut. If 2 points in our universe, say Earth and a planet orbiting Alpha Centauri, are very far apart on our brane, they might be very close together if you could travel through the bulk. It's a spaceship that could momentarily pop off our brane, travel a short distance through the 5th dimension, and pop back onto our brane at its destination could effectively travel faster than light. This would not be a warp drive, but a hyperspace jump. It would also require unimaginable technology. You would need to be able to manipulate the boundary between our universe and the bulk, and to navigate in a higher dimensional space. These ideas are highly speculative, but they show how the existence of extra dimensions could fundamentally change our understanding of what is possible. The cosmic speed limit might not be an absolute law, but a local bylaw that only applies to those of us stuck on the brain. Number 8, some fundamental forces might not be fundamental at all. In 1919, Theodore Kaluza sent a paper to Albert Einstein showing that if you write the equations of general relativity in 5 space-time dimensions, they naturally split into 2 parts: Einstein's original 4D equations for gravity and Maxwell's equations for the electromagnetic force. Oscar Klein later refined this in 1926 by suggesting the 5th dimension was curled up into a tiny circle. The strong and weak nuclear forces were not discovered until the 1930s and later, so they were not part of this original unification. We have 4 known fundamental forces of nature, gravity, electromagnetism: the weak nuclear force responsible for radioactive decay, and the strong nuclear force which holds atomic nuclei together. For the last century, a major goal of physics has been to unify these forces to show that they are all different aspects of a single underlying force. James Clerk, Maxwell unified electricity and magnetism in the 19th century. In the 20th century, the electromagnetic and weak forces were unified into the electroweak force. The standard model of particle physics describes the electroweak and strong forces in a common mathematical language, but it does not truly unify them. Gravity remains the odd one out. M-theory provides a framework for unifying all 4 forces, and it does so through the geometry of extra dimensions. The original Kaluza-Klein theory was the first hint of how this could work. It showed that a force we see in our 4D world, electromagnetism, could simply be the effect of gravity in a 5D world. The components of the 5D gravitational field that operate in our familiar dimensions create what we call gravity. But the components that operate between our dimensions and the extra, curled up 5th dimension create what we call the electromagnetic field. The photon, the particle of light, is just a ripple in the geometry of the 5th dimension. This is a breathtaking idea. A force that seems completely distinct and fundamental is revealed to be a manifestation of the geometry of a hidden dimension. M-theory extends this idea to all the forces. To accommodate the strong and weak forces, you need more than one extra dimension. You need a complex, multi-dimensional shape for the curled-up space. In this picture, the different forces are different kinds of ripples in the geometry of the various extra dimensions. The properties of the forces are determined by the symmetries of this internal space. The particles that carry the forces, the photon for electromagnetism, the W and Z bosons for the weak force, the gluons for the strong force, are all different vibrational modes of the higher dimensional gravitational field, or different types of strings vibrating in these dimensions. So, the fundamental forces we observe may not be fundamental at all. They are geometric effects. The reason electromagnetism is so much stronger than gravity is, in this original picture, related to the tiny size of the extra dimension. The reason the strong and weak forces operate only over very short distances is related to the specific geometry of the dimensions they are associated with. This provides a path to a theory of everything. If we could figure out the exact shape of the 6 or 7 compactified dimensions, we could, in principle, calculate the properties of all the forces and all the particles from first principles. The search for this correct Calabi-Yau manifold is a major area of research in string theory. There are many possibilities, which leads to the landscape problem, but the core idea remains. The rich and complex tapestry of forces that governs our universe might be nothing more than the geometric echoes of dimensions we can never see. Number 7, the universe may have more than 3 generations of matter. There are 3 known generations or families of matter particles. The first generation includes the up quark, the down quark, and the electron, which make up all normal matter. The second and third generations are heavier, unstable copies, muon, tau, strange, quark, etc. In 1989, experiments at the Large Electron-Positron Collider LEP at CERN measured the decay of the Z boson and showed with high precision that there are only 3 generations of light neutrinos, which strongly implies there are only 3 generations of matter. The matter in our universe seems to come with a strange sense of repetition. The particles that make up everything around us, the up quark, the down quark, and the electron, are just the first in a series of 3. There is a second generation of particles, which are identical to the first in every way except they are heavier. It includes the strange quark, the charm quark, and the muon. Then there is a third, even heavier generation, the bottom quark, the top quark, and the tau. These heavier particles are all unstable. They were present in the early universe, but quickly decayed into the lighter first-generation particles. We can only create them today in high-energy particle accelerators. This threefold repetition is a deep mystery of the Standard Model. Why 3 generations? Why not just 1? Or 5? Or 10? The Standard Model provides no answer. It is just a number that we have to put in by hand based on experimental observation. M-theory's geometric approach offers a possible explanation. The number of generations of matter is not a random number. It is a topological property of the hidden compactified dimensions. It is related to the number of holes in the Calabi-Yau manifold. To understand this, think of a simpler shape, like a donut, a torus. A donut has 1 hole. A coffee mug, topologically, is the same thing. Now think of a sphere. It has no holes. A more complex shape could have multiple holes. In topology, this is measured by something called an Euler characteristic, or by Betti numbers. These numbers are integers that describe the fundamental shape of a space, regardless of how it is stretched or bent. In many string theory models, the number of generations of particles that appear in our 4D universe is directly related to these topological numbers of the 6D Calabi-Yau manifold. For example, the number of families might be equal to half the absolute value of the Euler characteristic of the manifold. This means that if we could find the one true Calabi-Yau manifold that describes our universe, we would be able to calculate the number of generations from its geometry. Physicists have found examples of manifolds that give exactly 3 generations. The problem is, they have also found many other examples that give 4 or 10 or hundreds of generations. This is again tied to the landscape problem, but it turns the question around. The fact that we observe 3 generations is a powerful clue about the shape of the hidden dimensions. It tells us that whatever the shape is, it must have the right kind of topological complexity to produce the number 3. Could there be a 4th generation of matter? The experiments at LEP seem to have ruled it out, but they only ruled out a 4th generation with a light neutrino. If a 4th generation neutrino were very heavy, which would be unusual but not impossible, it could have escaped detection. Searches for heavy 4th generation quarks are ongoing at the LHC. Finding such particles would be a revolutionary discovery. In the context of M-theory, it would send theorists back to their blackboards, searching for a new class of Calabi-Yau manifolds with a different number of holes, a different fundamental geometry for the hidden space that defines our reality. Number 6. We can't find the Higgs boson's true mass. The Higgs boson was discovered at the LHC in 2012 with a mass of about 125 GeV giga electron volts. According to quantum field theory, the Higgs mass should be driven up to the Planck scale, around 10 raised to the power of 19 GeV by quantum corrections. This discrepancy is a version of the hierarchy problem, sometimes called the Higgs mass naturalness problem. Supersymmetry, a key component of M-theory, predicts a partner particle for every known particle, and the interactions between these partners can cancel out the problematic quantum corrections. The discovery of the Higgs boson was a triumph for the Standard Model. The Higgs field gives fundamental particles their mass, and the Higgs boson is the particle associated with this field. But the mass of the Higgs boson itself is a profound puzzle. It is about 125 GeV. The problem is that in our current theories, this value is not stable. Quantum mechanics tells us that empty space is not really empty. It is a bubbling, seething foam of virtual particles that pop in and out of existence for fleeting moments. These virtual particles interact with the Higgs boson, and these interactions should add energy and therefore mass to it. When physicists calculate the size of these quantum corrections, they get a ridiculously large number. The corrections should drive the Higgs mass all the way up to the Planck scale, which is about 10 quadrillion times larger than the measured value. To get the observed mass of 125 GeV, the bar mass of the Higgs, in the theory must be set to a value that cancels out these enormous quantum corrections with an incredible, almost perfect precision. It is like having two numbers, both the size of a continent, that subtract from each other to leave a result the size of a grain of sand. This fine-tuning seems incredibly unnatural to physicists. It suggests that there is some new physics we are missing, some mechanism that protects the Higgs mass and keeps it light. One of the most popular solutions is supersymmetry SUSY. Supersymmetry is a principle that proposes a deep symmetry between the two basic types of particles in the universe, fermions matter particles like electrons and quarks, and bosons force-carrying particles like photons, and the Higgs boson. It predicts that every known particle has a superpartner. Every fermion has a corresponding boson partner, e.g., the electron's partner is the selectron, and every boson has a corresponding fermion partner, e.g., the photon's partner is the photino. Supersymmetry is a crucial ingredient in M theory. It is what makes the math work and keeps the theory stable. And it provides a beautiful solution to the Higgs mass problem. The quantum corrections from the normal particles which drive the Higgs mass up are almost perfectly canceled out by equal and opposite corrections from their superpartners. The cancellation is not perfect, which is why the Higgs still has some mass, but it solves the fine-tuning problem. The Higgs mass is naturally kept small. If supersymmetry is real, where are all these superparticles? We have never seen one. The theory suggests they must be much heavier than their standard model partners, which is why we have not created them in our accelerators yet. One of the main goals of the Large Hadron Collider is to search for these supersymmetric particles. They would be created in the high-energy proton collisions and would then decay in specific ways, leaving signatures like missing energy if they decay into a stable, invisible particle, which could be dark matter or an excess of other specific particles. So far, the LHC has found no evidence for supersymmetry. This has forced physicists to reconsider their models. It could be that the superpartners are even heavier than originally thought, just beyond the reach of the current machine. Or it could be that the solution to the hierarchy problem lies elsewhere. But if M theory is the right direction, then some form of supersymmetry must be a feature of our universe. The stability of the Higgs boson, the particle that gives our world mass and substance, could depend on a whole shadow world of supersymmetric partners vibrating in the hidden dimensions all around us. Number 5, the universe should not have a preferred direction, but it might. The axis of evil is a term coined by physicists Kate Land and João Magejo to describe a series of unexpected alignments seen in the temperature fluctuations of the cosmic microwave background. The plane of our solar system, the ecliptic, and the plane of our own Milky Way galaxy are surprisingly aligned with some of the largest scale features of the CMB. The probability of this occurring by chance is estimated to be less than 0.1%. A fundamental assumption in cosmology is the cosmological principle. It states that on large scales, the universe is homogeneous, the same everywhere, and isotropic, the same in every direction. There should be no special places and no special directions. The universe should look statistically the same, whether you look towards the constellation of Orion or the constellation of Ursa Major. The cosmic microwave background provides the best test of this principle. It is a map of the universe in its infancy, and it should be perfectly isotropic except for random quantum fluctuations. And for the most part, it is. The pattern of hot and cold spots looks very random, as predicted. But when scientists from the Map and Planck satellite missions analyzed the maps with extreme precision, they found some strange anomalies. Several of the largest scale patterns in the CMB, the quadrupole and octupole moments, which describe the broadest temperature variations across the whole sky, seem to be aligned with each other. And more bizarrely, they seem to be aligned with the plane of our own solar system, the ecliptic. This alignment has been dubbed the axis of evil, because it threatens to undermine our most basic cosmological assumptions. It is a deeply strange result. Why should the largest features in the entire observable universe, patterns set in stone 13.8 billion years ago, have any relationship to the orientation of our local solar system, which formed just 4.5 billion years ago? It seems like a wild coincidence. Most cosmologists believe it is just that, a statistical fluke that will go away with better data or analysis. But the anomaly has stubbornly refused to disappear. Some more exotic theories propose that this might be a real physical effect, a sign that the universe is not perfectly isotropic. The geometry of the extra dimensions in M theory could be a source for this. The standard assumption is that when the extra dimensions are compactified, they are curled up in the same way at every point in our large 3D space. But what if they are not? What if there is a slight variation, a gradient, in the shape or size of the extra dimensions across the vast expanse of our universe? For example, the volume of the Calabi-Yau manifold could be slightly larger in one direction of the universe than in the other. Since the properties of physics, like the strength of forces, depend on this volume, this would create a subtle anisotropy. The laws of physics would be slightly different in one direction of the sky than in another. This could have an effect on the CMB if the universe expanded at a slightly different rate in different directions, a so-called anisotropic expansion. It would stretch the patterns in the CMB and could create the kind of alignments that we see. The axis of evil might be pointing in a direction related to a gradient in the geometry of the hidden dimensions. This is a highly speculative idea. It would mean that the cosmological principle is not fundamentally true. The universe does have a preferred direction, a cosmic grain, inherited from the underlying geometry of its unseen dimensions. Testing this would be very difficult. It would require looking for other independent signs of anisotropy in the distribution of distant galaxies or in the polarization of light from quasars. But it remains a possibility that this strange alignment in our sky is a faint echo of a geometric truth about the universe that is far grander and stranger than we imagined. Number 4, the force of gravity itself might have mass. General relativity predicts that gravitons, the hypothetical particles of gravity, are massless. This is why gravity has an infinite range. A 2017 analysis of gravitational waves detected by LIGO from merging black holes confirmed that the graviton's mass must be incredibly small, less than 7.7 x 10 raised to the power of 23 electron volts. If the graviton had mass, gravitational waves would travel slightly slower than the speed of light, and the speed would depend on their frequency. In Einstein's theory of general relativity, gravity is a consequence of the curvature of space-time. The particle associated with this force, the graviton, is predicted to be massless. Just as the photon is a massless particle that travels at the speed of light, the graviton should be a massless particle that travels at the speed of light. Its masslessness is why gravity, like electromagnetism, has an infinite range, but some theories that try to modify gravity or unify it with other forces suggest that the graviton might have a tiny non-zero mass. This would fundamentally change the nature of gravity. It would mean that gravity is a short-range force. Its influence would still extend over vast cosmic distances, but it would get weaker even faster than the inverse square law predicts at the very largest scales. This could have implications for explaining the accelerated expansion of the universe without needing dark energy. M theory provides a natural mechanism for how the graviton could acquire a mass. This comes from the brane world scenario, particularly in the Randall-Sundrum models. In these models, our universe is a brane in a higher dimensional space-time. The normal massless graviton is a wave that can travel in the bulk. But because of the presence of the brane and the warped geometry, like there can also be other modes of vibration. These are the Kaluza-Klein KK gravitons. From our 4D perspective on the brane, these higher dimensional vibrations appear as massive particles. So in addition to the standard massless graviton, the theory predicts a whole tower of massive gravitons. The first of these KK gravitons could be light enough to be produced at the LHC, which is what experiments are looking for when they search for resonances decaying into pairs of particles. But there is another possibility. In some more complex, massive gravity theories, the graviton we experience in our 4D world could itself be a massive mode. It could be a resonance that is localized on our brane. The idea is that gravity is fundamentally a higher dimensional force, but our brane creates a kind of potential well that traps gravitons near it. This trapping is not perfect. A trapped graviton would have a tiny mass and would be able to slowly leak into the extra dimensions. If the graviton has mass, it would have observable consequences. One is that gravitational waves would not travel at exactly the speed of light. They would travel slightly slower, and, just like light passing through a prism, a gravitational wave made of massive gravitons would experience dispersion. Higher frequency waves would travel at a slightly different speed than lower frequency waves. The detection of gravitational waves from merging neutron stars in 2017 provided a spectacular test of this. Light gamma rays and gravitational waves were seen from the same event. They arrived at Earth after traveling for 130 million years within 1.7 seconds of each other. This incredible synchronicity places extremely tight constraints on any difference between the speed of gravity and the speed of light. It tells us that if the graviton has a mass, it must be astonishingly small. While these observations have ruled out many simple massive gravity theories, they have not eliminated all possibilities. The extra dimensions of M theory provide a rich and complex environment where the graviton could have a subtle mass that is consistent with observations. The very nature of gravity, the oldest and most familiar force, might be tied to its existence as a massive particle bound to our dimensional membrane. Number 3, magnetic monopoles should exist, and they could be hidden. The theory of magnetic monopoles, isolated north or south magnetic poles ring, was first proposed by Paul Dirac in 1931. He showed that the existence of a single magnetic monopole in the universe would explain why electric charge is quantized, comes in discrete units. Grand unified theories, GUTs, predict that a huge number of magnetic monopoles should have been created in the early universe, but none have ever been found. This is known as the magnetic monopole problem. Every magnet we have ever seen has two poles, a north and a south. If you cut a bar magnet in half, you do not get a separate north pole and a separate south pole. You get two smaller magnets, each with its own north and south pole, but there is no fundamental reason why this has to be the case. The equations of electromagnetism would be more symmetric if there were also magnetic charges or magnetic monopoles. The existence of monopoles is strongly predicted by any theory that seeks to unify the fundamental forces. These grand unified theories predict that in the extreme heat of the very early universe, monopoles should have been created in copious numbers. As the universe cooled, these monopoles should have been frozen in. Based on these theories, the universe should be teeming with them. They would be very massive, stable particles. Yet, despite decades of searching with dedicated experiments, not a single convincing magnetic monopole has ever been detected. This is a major puzzle. M theory and the geometry of extra dimensions offer a place for these monopoles to hide. In some string theory constructions, magnetic monopoles are not point particles in our 3D space. Instead, they are the ends of branes from a higher dimension that are piercing our own brane. Imagine our 3D universe is a sheet of paper. A one-dimensional string or a two-dimensional membrane from the bulk could pass through our sheet. The point where it intersects our universe would look, to us, like a particle, and the properties of this intersection point would depend on the properties of the higher dimensional object. It turns out that in some of these models, the end of a specific type of brane intersecting our world would have exactly the properties of a magnetic monopole. This provides a different picture of what these elusive particles are. They are not just heavy point particles, they are points of connection to a larger dimensional structure. This idea can also help explain why they are so rare. The energy required to create one might not just be the energy to create its mass, but the energy required to create the entire brane structure attached to it, stretching out into the extra dimensions. Another idea is that the monopoles were created, but they live on a different brane than us. If there is a parallel magnetic brane very close to our own electric brane, where our familiar matter resides, then monopoles could exist in vast numbers just a short distance away in the bulk. We would not be able to detect them directly, but we might feel their gravitational influence. They can even be a component of dark matter. This also ties into a deep concept in string theory called S-duality. S-duality is a symmetry that relates a theory with a strong force to another theory with a weak force. In many cases, it exchanges electric charges with magnetic charges. A fundamental particle with electric charge in one theory, like an electron, becomes a composite magnetic monopole in the dual theory, and vice versa. This suggests that electric and magnetic charge are two sides of the same coin, and their true nature is only revealed in the full context of M-theory's extra dimensions. The missing monopoles might not be missing at all, just transformed or hidden in a way we cannot yet perceive. Number 2, the end of the universe might be a big rip driven by extra dimensions. The Big Rip is a hypothetical end-of-the-universe scenario first proposed in 2003 by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg. It is caused by a type of dark energy called phantom energy, which has an equation of state parameter W less than 1. Current observations from the Planck satellite constrain WO to be very close to 1, but do not rule out the possibility that it is slightly less. We know the universe is expanding, and that this expansion is accelerating due to dark energy. The ultimate fate of the universe depends on the exact nature of this dark energy. If it is a cosmological constant, as in the standard model, the expansion will continue forever, and the universe will end in a cold, dark, empty state known as the heat death or big freeze. But what if dark energy is not constant? What if its density increases over time? This would lead to a much more violent end. This type of energy is called phantom energy. If phantom energy exists, the repulsive force it generates would grow stronger and stronger. The acceleration would not be gentle, it would be runaway. This leads to a scenario called the Big Rip. In the final stages of a Big Rip, the expansion would become so powerful that it would overcome all the other forces of nature. A few 100 million years before the end, the phantom energy would be strong enough to unbind the Milky Way galaxy, sending all its stars flying apart. A few months before the end, it would overcome the gravity holding our solar system together. The Earth would be torn away from the sun. In the final minutes, the Earth itself would be ripped apart. In the last fraction of a second, atoms would be torn asunder. The end would come as the expansion rate becomes infinite, ripping the very fabric of space-time apart. This sounds like a fantastical horror story, but it is a physically possible consequence of general relativity if phantom energy exists. The problem is that phantom energy is very strange stuff. It violates certain energy conditions that are usually assumed to hold true. It has a negative kinetic energy, which can lead to instabilities in the vacuum. Brane world models, however, provide a way to get this kind of behavior without needing true phantom energy. The observed acceleration of our universe might not be caused by a strange energy field on our brane at all. It could be a higher dimensional effect. In some models, the expansion of our 3D brane is tied to the movement of our brane through the 5D bulk. It is possible to construct scenarios where gravity from the bulk causes our brain to accelerate in a way that mimics phantom energy. From our perspective, it would look exactly like a big rip is coming. The effect of dark energy on our brain would appear to be growing, leading to a runaway expansion. But the cause would be external. It would be the interaction of our universe with the higher dimensional space it is embedded in. In one such model proposed by Paul Frampton, this big rip is avoided at the last moment when the universe breaks up into a series of causally disconnected patches, each of which undergoes its own rebirth in a kind of cyclic process. The possibility of a big rip, driven by the geometry and dynamics of unseen dimensions, is a stark reminder of how our cosmic destiny could be tied to physics beyond our direct perception. The same extra dimensions that may have sparked our universe's birth in a brane collision could also be the architects of its ultimate violent destruction. Number one, information from before the Big Bang could exist today. The standard Big Bang model with inflation erases any information about what might have come before it. The exponential expansion smooths everything out, leaving a blank slate. In cyclic or ekpyrotic models, the universe goes through a bounce rather than a singularity, which allows for the possibility of information surviving from one cosmic cycle to the next. A 2015 paper by Roger Penrose and Vahey Gurzadian claimed to find evidence of Hawking Point's apse remnants of black holes from a previous cosmic aeon in the CMB data, though this claim is highly disputed. The question of what came before the Big Bang has long been considered outside the realm of science, a question for metaphysics or religion. In the standard cosmological model, it is a meaningless question. The Big Bang was the beginning of time and space. There was no before. Inflation, the period of super fast expansion in the first moments, effectively resets the universe, wiping clean any evidence of the initial conditions. But models that involve extra dimensions, like the cyclic ekpyrotic model, change the picture entirely. In this view, the Big Bang was not a beginning, but a transition. It was the moment our brain collided with another, converting the kinetic energy of the collision into the matter and radiation of a new cosmic cycle. The universe existed before the bang, in a long, cold, contracting phase. This raises a tantalizing possibility: could information from the previous cycle, the universe that existed before ours, have survived the bounce? The collision, or bounce, is an extreme event. Most structures would be destroyed, but some subtle correlations or imprints might be able to make it through. The details of the bounce are governed by the physics of the extra dimensions. The nature of the force between the branes and the way they interact determines how hard or soft the bounce is. If the bounce is gentle enough, it is possible that large-scale structures from the previous universe could leave a faint imprint on the new one. For example, fluctuations in the fields on the branes during the contracting phase could pass through the bounce and become the seeds for the temperature fluctuations we see in the cosmic microwave background. If this were true, it would mean that some of the largest patterns in our sky are not random quantum fluctuations from inflation. They are relics, ghosts from a previous cosmic aeon. Looking at the CMB would be like looking at a palimpsest, a manuscript where an old text has been scraped off and a new one written over it, but faint traces of the original writing remain. This has led to some speculative but fascinating searches in the CMB data. Roger Penrose's conformal cyclic cosmology, which is not a brane model but shares the idea of cycles, predicts that supermassive black holes from a previous aeon would leave faint, circular, low-variance rings in the CMB of our aeon. His team has claimed to find such features, but the statistical significance is a subject of intense debate among cosmologists. The idea that information can survive the Big Bang is perhaps the most profound implication of these higher-dimensional models. It would transform cosmology. The Big Bang would no longer be an ultimate barrier to our knowledge. We could, in principle, look back beyond it. the extra dimensions would not just be a hidden feature of our current universe, they would be the bridge connecting us to a past that is older than time itself as we know it. They would be the conduits of cosmic memory.